Greetings to all. I am Daisy, and I will be the webinar moderator. Welcome to the 8th Masterclass Series webinar of OMS eLearning Academy. Today's webinar topic is model-based real-time tracking of tanks qualities. We have an overwhelming response of 60 plus registrations from 40 countries and welcome you all. And hope you all will have a very informational and interactive session today. Before we start, let me discuss a few house rules. The webinar will be 40 to 45 minutes long with a 10-minute Q&A session. You can enter your question in the chat box during the presentation, which will be answered at the end. The webinar will be recorded and available on the OMS eLearning Academy website. There will be a 2-question poll at the end for your input. Please give us your candid feedback at the end via the redirected Google form. Today's webinar speaker is Dr. Suresh Agrawal, the founder and CEO of Offsite Management Systems LLC, and Academy Director of OMS eLearning Academy. Offsite Management Systems LLC was founded in 1998 in Houston, Texas. It's chartered to provide consulting and refinery automation project executions worldwide. OMS eLearning Academy was founded in 2018 to provide continuing education to professionals working in the downstream refining industry and related businesses via the eLearning platform. The Academy has 200 plus courses that can be taken online anytime, anywhere, and on any device. You will learn 3 ideas of strategic model-based real-time tracking of tanks qualities in this webinar. 1. Modes of quality analysis. 2. Economics of quality analysis. And 3. A case study. Thank you all for attending this informative webinar. To appreciate your efforts, we have 2 complimentary gifts for you. Please stay until the end to learn about them. With this, let me request today's speaker, Dr. Agrawal, to start the webinar. I will be back at the end of the presentation. Thank you.
This online seminar will explore various facets of tank quality management. We will start with a general overview of different plant areas and their roles in product quality management. Then, we will delve into the methods utilized to estimate the quality of the managed or produced products. A critical component we will examine is the load and associated costs of laboratory analyses, which are essential for ensuring product quality. Furthermore, we will discuss the economics of implementing online tank pseudo-analyzers, a technological approach to streamline quality control. We will also provide a real-world example of how these applications are deployed in industrial settings. This will lead us to examine the specific features of the systems used and their performance, all of which will be substantiated by data from a case study. Lastly, we will summarize the critical points of this discussion, ensuring you have a clear understanding of the value and impact of these technologies and methodologies in real-time tracking of tank qualities. This overview is designed to give you a comprehensive picture of the latest strategies for managing and improving product quality in industrial plant operations. Let us take a closer look at the layout of a typical plant tank farm, an essential hub in the refining process. Refineries are strategically organized into 4 critical operational areas. On-site operations, labeled Area 3, are the heart of the manufacturing process, focusing on creating intermediate products. On the other hand, off-site operations, which cover Areas 1, 2, and 4, are vital for managing the refinery's inputs and outputs. Area 1 is where feed preparation occurs, receiving crude and feedstocks. This is followed by Area 2, the tank farm itself, a pivotal junction for storage and further processing. Area 4 is dedicated to product preparation before dispatch. Areas 1 and 2 form what we call the refinery's fence line. This is where the entire cycle from receipt to dispatch of products is managed. It is a crucial buffer zone managing the flow in and out of the refinery. The off-site areas are particularly significant commercially. They are the refinery's profit generators, managing the saleable end products. These off-site operations sharply contrast with the on-site processes, which focus on transforming crude into valuable final products. Understanding the dynamics of these areas helps us appreciate the refinery's workflow and the importance of real-time tracking of tank qualities, which ensures efficiency and profitability in this complex operation. Quality analysis is pivotal in refinery operations and can be conducted through various modes and methods. Three primary methods are employed to measure or estimate product qualities within a refinery. Firstly, we have laboratory sampling, which remains the cornerstone of quality analysis. Lab analyses serve as a crucial backup and provide certification for all sample points, ensuring reliability in the measurement process. Secondly, there's online measurement. Although not all streams are equipped with online analyzers, they provide a continuous and real-time assessment of product quality for those who are. Lastly, we resort to model-based predictions when online measurement is not available. This method uses computational models or inferential techniques to estimate the quality of the streams. The slide clearly shows which methods are currently practiced and which are optionally practiced across different refinery areas, such as the fence line, the tank farm, and the process units. These methods form a comprehensive approach to managing quality, each with its role in ensuring the final products meet the set standards and specifications. Understanding and implementing these methods efficiently is critical to the success of any refinery operation. In today's discussion on refinery operations, we highlight three crucial tank information types required for optimal management and compliance: inventory, quality, and fugitive emission. Modern refineries leverage automated tank gauging systems for inventory to keep a real-time tab on their liquid assets. This technology is crucial in monitoring the transfer of materials between plants, managing crude and product blending, and handling custody transfers with precision. Regarding quality, we are looking at a robust certification process for product qualities before dispatch, thorough checks of feedstocks, and continuous control of process stream quality. This is further reinforced by comparing the readings from online analyzers to ensure consistency and accuracy. Lastly, we focus on fugitive emissions, an environmental and safety concern. Refineries can better adhere to local environmental regulations controlling air pollution and significantly minimize the risk of explosions by estimating vapors that escape from tanks during loading. Together, these components of tank information form a trifecta of refinery efficiency and safety, ensuring that operations meet industry standards and contribute to sustainable and responsible production. Now, let us dive into the sophisticated methodologies deployed for analyzing and estimating tank qualities within the refinery sector. First up, we have process analyzers. These are specialized devices, ranging from single-purpose analyzers for one specific analysis to integrated systems capable of multiple analyses, like near-infrared, NIR, or nuclear magnetic resonance, NMR, technologies. Some refineries utilize a combination of discrete and integrated analyzers or advanced multiplex systems that can manage multiple components and analyses simultaneously. Next, we look at lab analysis. This traditional and rigorous approach involves a structured sampling and analysis schedule, with process streams sampled more frequently than tanks. To ensure the accuracy of online analyzers, samples are also taken to the lab. Furthermore, refineries often participate in round-robin tests to certify their lab values, maintaining the highest quality verification standards. Lastly, model prediction plays a vital role. This prediction approach harnesses blend and inferential models' power to estimate tank and process stream qualities. It necessitates using multiplexed analyzers at tank inlets, allowing for a real-time model of tank qualities marrying historical data with new inputs to predict quality metrics accurately. These three methods represent the cutting edge in ensuring that the quality of the products stored in tanks is consistently monitored and maintained, reflecting the refinery's commitment to precision, safety, and quality control. In the meticulous field of quality assurance within refineries, we employ a multi-tiered system of checks and balances to mitigate errors and biases. Starting with process analyzers, these sophisticated equipment pieces are not immune to analyzer error bias, necessitating regular calibration and cross-verification to ensure precision. Lab analysis stands as the bedrock of quality verification. Despite its rigor, it, too, faces the possibility of human error. To counter this, we have stringent cross-checks and protocols, including participation in round-robin testing, a system-wide comparison exercise to ensure consistency and accuracy among various laboratories. Model prediction, utilizing historical and predictive data, also brings in its challenges with model error bias. Continuous refinement of models with new data is essential to keep this in check. These methods converge to form a robust network of error checking, with each method validating the others, ensuring that the data on tank qualities is dependable and validated across multiple platforms, thus maintaining the highest quality control standards. Let us delve into Method 1 for tracking tank qualities: crucial to maintaining high standards in refinery operations. First off, we have the online analyzers. These are critical tools positioned at strategic points such as the tank inlet or outlet, monitoring the quality of the streams in real time. This continuous analysis allows for immediate adjustments and ensures consistent product standards. The second layer of quality control comes from tank sample and lab analysis. Samples are regularly extracted from the tanks and analyzed in the lab to verify the online analyzer's readings. This dual approach reinforces the accuracy of the data we rely on. Finally, we integrate model-based predictive calculations. These sophisticated algorithms consider historical data, current measurements, and predictive analytics to estimate future tank qualities. This provides foresight and enables initiative-taking decision-making to maintain quality standards. By combining these three methods, we establish a robust, multifaceted approach to quality assurance that is both responsive and predictive, ensuring that our products meet the highest quality benchmarks before they reach the market. In the high-stakes process control and quality assurance environment, online process analyzers are the unsung heroes. Here is how they fit into the workflow. Firstly, we place these analyzers right on the process unit output streams. Their job: to measure the stream qualities meticulously, ensuring each product meets our stringent standards before it moves down the line. Secondly, we can deploy additional analyzers at the tank inlet. This step is not always used, but when it is, it provides an extra layer of quality control by measuring the qualities of the materials right as they enter the tank, keeping a vigilant eye on the process upstream from the process units. And thirdly, these analyzers also play a critical role in the tank outlet streams. They are our final checkpoint, ensuring that the qualities of the materials as they leave the tank are up to par. With these online process analyzers at strategic points, we are not just tracking quality, we are defining it in real time, ensuring every product that leaves our facility does so with a stamp of excellence. In our ongoing discussion on refining operations, let us focus on the role of online and lab analysis in monitoring the rundowns from process units. Online analyzers are installed at process units to provide immediate insight into the qualities of the rundown streams. However, it is critical to understand that these readings reflect the state of the product at that moment and location and not necessarily the quality at the destination header or the storage tank. These analyzers also cannot cover all bases. They do not analyze every quality aspect of a stream, so lab analysis comes into play to cover the full spectrum of required quality checks. Another interesting point to consider: these online analyzers are not always exclusive to a single stream. They may serve multiple streams, thus providing a shared service that is both efficient and practical. These online and lab analyses provide a comprehensive picture of product quality as it moves from the process units to the destination, ensuring we maintain the highest quality standards at every stage. The world of refinery operations heavily relies on the precision of online blending analyzers. Positioned at the critical junctures where components leave their tanks or at the blending header, these analyzers are the gatekeepers of quality during the blending process. They can be specialized for tasks or multifunctional, providing a dynamic assessment of various product streams. These analyzers spring to life when the blending process is active. During these periods, they meticulously measure the qualities of the mix. Without active blending, they remain dormant, conserving their capabilities for when the process recommences. However, it is essential to note that even these advanced tools do not extend their reach to measuring the final product qualities in the tank. For that, and for assessing tank qualities before the blending starts, lab analysis remains the cornerstone, providing the necessary depth and detail to ensure product integrity. Online blending analyzers offer a snapshot of the blending operation, part of a larger picture that ensures the quality of the product through a combination of sophisticated online tools and thorough laboratory work. In our exploration of gasoline blending, we turn to the critical role of conventional online analyzers. These systems are not one-size-fits-all. Different analyzers are used for different quality aspects. For instance, near-infrared (NIR) analyzers handle a variety of quality measures but are not used for sulfur content, which requires a specific type of analyzer. These online analyzers operate in a multiplexed fashion. What does that mean? It means they can cycle through multiple streams, assessing each to give a comprehensive overview of the qualities within the blending process. This setup feeds into an advanced blend control and optimization system, which relies on the analyzed qualities to make real-time predictions and adjustments, ensuring the final blended product meets the exact specifications required. This intricate dance of technology is vital to how modern refineries maintain consistent product quality at every stage. This slide presents the varied features of online process analyzers in refinery operations. Online process analyzers are the technological eyes within a refinery stationed at the exit points of process unit streams. This strategic placement allows them to capture real-time data essential to control unit operations. They are not just limited to monitoring the egress of streams but can also be found at the ingress points, such as the inlet to a storage tank, providing a versatile range of monitoring points. In the specific context of gasoline inline blending, these analyzers are indispensable. They are placed at the exits of tanks where they scrutinize the quality of products at this crucial juncture of production. Further versatility is noted in their installation at blend header inlets, which allows for a preemptive assessment of the qualities that will eventually define the final product. The design of these analyzers varies. They can be either discrete, handling a single quality measurement for one stream, or integrated, capable of analyzing multiple qualities in one go. Additionally, some are multiplexed, meaning they can alternate their attention between different streams, enhancing their utility and efficiency within the plant operations. Through these features, online process analyzers provide a comprehensive and dynamic picture of product qualities across the refinery, which is crucial for ensuring top-notch product standards. Method 2 provides a structured approach for ensuring product quality within the refinery space. Here is how it works. At the forefront, we have online analyzers strategically placed at the outlets of tanks or upstream of process units. These are our first line of defense, offering real-time data on the streams as they move through the refine. Next in our arsenal is the rigorous tank sample and lab analysis. In this case, the physical samples from the tanks are scrutinized in a lab setting. It is a meticulous process that complements the data from online analyzers, providing a level of detail invaluable for quality control. Lastly, we harness model-based predictive calculations. This predictive method is where the art of prediction comes in, blending historical data with current observations to forecast quality parameters, enabling proactive management of the refinery process. Together, these three elements form a comprehensive method for tracking and ensuring the quality of tank contents, blending the immediacy of online analysis with the depth of lab verification and the foresight of predictive modeling. This slide outlines a lab schedule that is instrumental for on-site refinery operations. In a laboratory setting within the refinery, every product and process stream from naphtha to visbreaker diesel has a dedicated schedule for sampling and analysis. This meticulous planning allows for precisely tracking the number of analyses required daily, weekly, and annually for each product. Such a detailed schedule is more than a mere timetable. It is a strategic framework designed to forecast laboratory operations workload and financial impact on the refinery. The refinery can perform a thorough cost and benefit analysis by looking at the frequency of analyses and the sheer number required across different streams annually. This proactive approach is about maintaining product integrity and optimizing operations for cost efficiency. This lab schedule is a vital tool in managing both the operational excellence and the economic performance of the refinery, ensuring that quality control is never compromised while keeping an eye on the bottom line. The cost of lab analysis is not arbitrary. It is determined by a precise formula: the number of source points sampled, the number of qualities analyzed per sample, and the number of samples taken per period. This analysis is neatly summed up as SSQ, a multiplying factor of these three variables. When considering the SSQ value, you look at the required lab work volume. A higher SSQ signifies a more significant laboratory workload and thus, a higher expense to the plant. To give you a perspective on costs, each SSQ typically costs about $15 to $20. This formula is not just a tool for accounting, it is a strategic asset that can be used for planning and optimizing lab operations to manage costs effectively while ensuring quality. Here, we highlight a lab schedule tailored for off-site refinery operations, highlighting a comprehensive list of products ranging from various types of naphtha to different diesel and kerosene components. Each product is meticulously scheduled for lab analysis with a specific frequency, ensuring that the off-site operations are monitored precisely as on-site activities. The detailed lab schedule indicates the number of annual analyses performed daily and cumulatively. These figures are not just for show, they are critical for calculating the load parameter SSQ, a formula Offsite Management Systems, OMS, developed to quantify the lab workload. By leveraging this schedule, the refinery can precisely determine the annual lab analysis load, represented by an impressive total of over 57,000. This data is a cornerstone for operational planning, enabling the refinery to forecast costs, allocate resources effectively, and maintain stringent quality control across all its off-site operations. Here is a breakdown of the SSQ, or source sample quality, across different refinery operations. This statistical approach, known as frequency distribution, highlights how often specific sample quality sequences occur. The table divides the data into three key segments: on-site, off-site, and overall refinery operations. B. By categorizing the SSQ values into bins, the refinery can quickly assess the distribution and frequency of sample analyses conducted. For instance, in off-site operations, the frequency with which specific SSQ values occur can vary significantly, with some sequences being much more common than others. This frequency distribution is vital for refining lab scheduling, workload estimation, and cost management. Overall, understanding this distribution aids the refinery in optimizing its sampling processes and aligning its lab activities with the operational demands, ensuring an efficient and cost-effective approach to maintaining product quality. This slide visually depicts the sample quality sequence, SSQ, workload across on-site and off-site refinery operations. The bar graph eloquently illustrates the frequency of lab analysis required per year at various SSQ intervals. This visual aid underscores a distinct contrast. On-site operations have a higher frequency of lab analyses, necessitating more frequent sampling, daily, in fact, to maintain stringent quality control. Off-site operations, while requiring a substantial number of samples, typically undergo weekly lab analyses. The takeaway is the SSQ parameter's capacity to offer a snapshot of the operational intensity. With this graphical representation, refinery managers can instantly gauge the lab workload and allocate resources efficiently, ensuring that the balance between operational demands and lab capacity is maintained optimally. This balance is crucial for sustained quality assurance in refinery production. Let us delve into the fiscal specifics of refinery lab analysis, presenting a detailed cost breakdown for on-site and off-site operations. This slide encapsulates the financial anatomy of lab work, offering a quantitative lens through which to view operational expenditures. It breaks down costs associated with the workforce for sampling and analysis and the overall yearly SSQ load, a key figure that echoes the volume of lab activity. In terms of expenditure, it is interesting to see how the total costs are distributed between sample collection and the lab analysis itself, underscoring the substantial investment a refinery makes to ensure product quality. Furthermore, the slide indicates that these costs can be honed to a near-precise estimate within a margin of plus or minus 10%. It is not set in stone. The flexibility is there to adjust local workforce costs, allowing refineries to fine-tune their budgeting with the real-time economic landscape. This cost analysis is more than a budget sheet. It is a strategic tool, empowering refinery management to allocate resources wisely and sustain their commitment to quality in the most cost-effective manner possible. Here, we introduce the concept of lumped bias contributions in tank quality tracking. This concept is crucial for understanding the various sources of inaccuracies that can impact the integrity of tank quality assessments. In essence, the total bias, phi-j, in any given quality measurement can be broken down into four contributing factors: the model bias from the blending process, phi-m, the interaction bias that may occur during the sampling or analysis, phi-a, the inherent bias from lab analyses, phi-l, and finally, any biases present in the final tank readings, phi-t. This equation allows refinery managers to dissect the total observed bias and pinpoint the root causes, ranging from the equipment used to the methodologies applied. It is a diagnostic tool that aids in refining the quality control process, ensuring that every factor is accounted for and that the quality of the product in the tanks is precisely monitored and maintained. Understanding and managing these biases is crucial to achieving the accuracy required for high-quality refinery outputs. Let us now discuss the process of estimating biases that can occur at different stages of tank quality analysis in a refinery setting. The flow chart begins with streamed samples that feed into lab analysis, where the potential for bias, phi-l, is accounted for, informed by results from periodic round-robin tests. These tests ensure lab measurements are as close to the actual value as possible. Simultaneously, online analyzers monitor the stream, subject to their own bias, phi-A. These biases are inherent to the devices and must be considered when interpreting their data. Then, we have the predicted blend header quality. This estimate includes its own model bias, phi-M, which arises from the predictive models used to forecast the qualities of the blend. Lastly, the final blend tank prediction carries a final bias, phi-T. This bias can stem from multiple sources and affects the final predicted quality of the product in the tank. Altogether, this estimation process is critical for identifying and minimizing biases throughout the refinery's operations, enhancing the accuracy of quality tracking, and ensuring the final product meets the desired specifications. Understanding and managing these biases ensures the quality control process is as precise and reliable as possible. Have you heard of round robin? It is a collaborative effort of multiple laboratories in a proficiency testing exercise known as round robin testing. This process is designed to enhance the accuracy and reliability of lab analyses across the industry. Here is how it works. A sample is first analyzed by a reference lab, which sets the standard for comparison. It is then passed along to the next lab in sequence, Lab A, initiating a cycle where each lab, in turn, assesses the same sample and sends its results to a central coordinating body. As the sample travels from lab to lab, each using potentially different instruments and methods, the coordinating body gathers the data. A comprehensive analysis is conducted once the cycle is complete and the sample returns to the coordinating body from the last lab. The final step is crucial. The coordinating body evaluates all results, adjusts for discrepancies, and generates a variance report. This report is critical to identifying deviations and helps all participating labs calibrate their methods and instruments, ensuring consistency and precision in future lab analyses. The round-robin exercise, therefore, is a testament to the collaborative efforts to uphold quality and accuracy in lab operations within the industry. Here is a visual comparison between online analysis and lab analysis for various properties of refinery products. Scatter plots show the relationship between the results obtained by online analyzers and those from lab analyses for sulfur content, 90% distillation point, flash point, and freeze point. Each plot displays data points representing individual measurements over time, plotting lab results against the corresponding online analysis results. These graphs highlight the variances, if any, between the two methods and provide a clear picture of their correlation and consistency. This graphical data can be a foundation for calibrating online analyzers and improving lab techniques, leading to more reliable and accurate product quality assessments. It is a compelling demonstration of how data visualization can fine-tune the intricate dance between various testing methodologies in a refinery context. Now, we focus on the critical role and features of tank samples and lab analysis within the refinery's operations. The schedule for taking these samples is meticulously predetermined, hinging on how crucial the tank quality data is for the refinery's workflow and for meeting the customer specifications. The information gained from these samples is essential. Not only does it form the basis for certifying the tank for final product sale, but it is also instrumental in planning how to blend various products like gasoline, diesel, or other fuels. Moreover, understanding the input feed qualities is necessary for the optimal operation of process units. However, there is a catch: results from these analyses are not instantaneous. They can take 4 to 24 hours to get to the teams that need them. And, if the tank is actively in use, the data may become outdated quickly, adding a layer of complexity to the refinery's decision-making process. While lab analyses are a cornerstone of product certification and quality assurance, refineries must navigate the time-sensitive nature of these results and their potential to become outdated in a dynamic production environment. Here is an outline of a 3-tiered approach for analyzing refinery tank qualities, incorporating the latest methodologies in data-driven decision-making. The first layer involves using online analyzers at critical junctures such as tank outlets or upstream process units. These sophisticated devices immediately read the product's qualities, providing crucial real-time data. Next, we have the tank sample and lab analysis phase. This step adds depth and verification to the data gathered by the online analyzers. It is about getting hands-on with the product and ensuring all quality parameters are met through rigorous testing. And finally, we bring in model-based predictive calculations. This method is where we take all the gathered data and apply advanced algorithms to predict future qualities. It is a forward-looking approach that helps anticipate and solve quality issues before they arise. Together, this trio of techniques ensures that quality control is not just about responding to current conditions but proactively managing the future, ensuring consistent product quality in the dynamic environment of a refinery. This slide illustrates the sophistication of model-based systems in monitoring and predicting tank qualities in refineries. This system is like the refinery's central nervous system, continuously analyzing and providing crucial quality data on the components and the final product tanks. The system can deliver near-instantaneous quality readings by integrating real-time tracking and advanced predictive algorithms. This technology does not operate in isolation. It communicates seamlessly with every part of the refinery operation, from the upstream process units to the downstream planners and even the online blending systems. This strategy ensures that every decision made, whether for blending or distribution, is informed by the most current and accurate data. The system is a pivotal tool for operational efficiency, product quality assurance, and decision-making optimization, underpinning the refinery's commitment to delivering high-quality products. Here, we highlight the economic impact of implementing model-based quality estimation for tank qualities in a refinery. It is a before and after snapshot of operational costs, revealing significant savings post-implementation. Initially, the process required half a sample per tank daily, with each sample undergoing 8 quality lab analyses. After transitioning to a model-based system, the number of analyses per sample is reduced, leading to fewer samples needed daily, translating to a substantial decrease in the daily and annual cost of operations. The standout figure here is the yearly savings, amounting to over $1 million, a testament to the cost-effectiveness of the model-based approach. But it is not just about savings. The return on investment, ROI, period is just 1.6 months. That is incredibly fast and a clear indicator of how swiftly the investment. This level of cost efficiency underscores the strategic value of model-based systems. Refineries can achieve a leaner, more economically sound operation by optimizing processes and reducing labor and resource expenditure. This slide delves into integrating a feed-forward system for tank qualities within process units in a refinery. It is a real-time operational hub, the tank's quality tracking system, which forms the centerpiece of this schematic. Here, we have a comprehensive setup where quality data from the tanks flows directly into the system. This setup is not just about raw data, it has been analyzed and prepped, ready to inform decisions. Everything from online analyzers to lab analyses and tank gauging data feeds into this system. This information is crucial because it informs the refinery-wide planning system and the online blend control and optimization system, which ensure that the blends meet quality standards and regulatory requirements. This diagram is a testament to how interconnected modern refinery operations are. The process relies on timely and accurate quality data from upstream to downstream. It is all about making informed decisions quickly, reducing waste, and maximizing efficiency. The system forecasts the quality of the product, ensuring that what eventually makes it to market is of the highest standard. Let us discuss a case study of an open-loop diesel rundown, a process within a refinery's diesel blending system. The slide features an intricate diagram showing the diesel rundown blending system overview, labeled with various components and process lines. The diagram highlights the complexity and precision required in the blending process. This system includes 3 blend headers, essential for managing the different diesel grades and specifications. The process streams feeding these headers are not siloed, they are interchanged as needed, offering flexibility and efficiency in operations. Quality control is critical in this process, and it is managed through a combination of online analyzers and offline lab analysis, ensuring that the diesel meets the necessary specifications for each blend. The online analyzers provide a continuous data stream, allowing for real-time adjustments. At the same time, the lab analysis offers deeper scrutiny to verify the product's quality before it is sent to the market. This slide encapsulates the detailed attention to quality and the use of advanced technology, ensuring that the final diesel product is consistent and meets the high standards expected by customers and regulators. We continue the discussion on the case study of the Kero rundown, an open-loop system pivotal in the blending of kerosene and jet fuel. This detailed system diagram underscores 2 key blend headers, illustrating the integration of multiple streams that converge into these headers, ensuring a harmonized and efficient blending process. Quality assessment in this system is a dual process. It employs both real-time online analyzers and periodic offline lab analyses, balancing the need for immediate data with the comprehensive scrutiny of laboratory precision. This method ensures that the kerosene and jet fuel qualities are consistently monitored and meet the stringent standards required for these products. The image is a testament to the refinery's commitment to maintaining optimal quality control throughout the blending process, enabling precise adjustments, and ensuring the integrity of the product. This advanced system highlights the refinery's capacity to adapt and respond to the dynamic demands of fuel quality management. Here, we present an insightful glance into the closed-loop gasoline blending process. This sophisticated system comprises 6 distinct component tanks, each integral to formulating the final gasoline product. The key takeaway here is the meticulous measurement of the quality of each component. In contrast, the tank's qualities are ascertained through rigorous offline laboratory analyses to ensure precision, and the collective product quality undergoes real-time assessment at the blend header through advanced online analyzers. This blending overview illustrates the technology and infrastructure in place and the refinery's commitment to precision and control. It captures the essence of modern refining, a balance of scientific analysis and real-time data processing, ensuring every drop of gasoline meets the set standards for quality and consistency. This system reflects a stride toward operational excellence, where technology bridges the gap between quality control and efficiency. Let us look at the dynamics of an open-loop gasoline blending process. Though adept in its function, this system encounters certain limitations, particularly its inability to loop back and autocorrect the flow and quality setpoints of the rundown streams. The operators are in the driver's seat, manually fine-tuning setpoints without automated feedback, akin to navigating without a map. However, this is where the ingenuity of the real-time tank quality tracking system, GOMS-TQTS, shines through. It serves as the compass for operators, providing crucial directional cues to fine-tune the process streams effectively. This method ensures that the most current and accurate data guides the blending process despite the open-loop system's inherent restrictions. This step leads to optimized blend qualities and a superior product reaching the market. Here, we will discuss another case study of an open-loop rundown blending system with one analyzer at the header with no feedback. This slide highlights cutting-edge advancements in analytical technology by introducing a new Raman analyzer juxtaposed with the existing analyzer models. This new addition to the instrumentation lineup is a testament to the continuous innovation in process monitoring. It offers enhanced capabilities for sampling and analyzing the component qualities in a multiplexing fashion, embracing the intricacies of slow-loop sampling right at the blend header and the precision required for fast-loop blend line sampling. This dual approach harmonizes the detailed, meticulous analysis of components with the dynamic, on-the-fly assessments needed for blend line analysis. It is like having a meticulous scientist and a quick-thinking strategist working to ensure that the rundown blend tank's output meets stringent quality expectations. With such technology, refineries are not just equipped but empowered to maintain the highest standards in product quality, thereby assuring customer satisfaction and regulatory compliance. We will further discuss the sophisticated realm of blend control, highlighting a dual approach with feed-forward and feedback mechanisms. It introduces the Modkin AI-based online blend control as a pioneering force in blend management, proactively setting flow targets for the blend components up front. It is an anticipatory move, like a chef who knows how much spice to add before the dish reaches the table. The data collector is the hub of this operation, gathering critical inputs such as flow rates, analyzer quality data, and lab analysis results. These inputs feed into the AI system that determines the rundown blend targets, which are then fine-tuned through an offline optimizer. This optimizer adjusts the recipe, accounting for optional steps like adding trim blending tanks, which refine the final product to meet precise specifications. What comes out of this intricate process is an optimized blend, ready to be stored or transported directly to the customer, such as a truck terminal. It is a delicate balance between what is measured and predicted on the fly and the calculated corrections applied offline, ensuring that the final product is not just up to mark but consistent and reliable, time after time. Here is another example of naphtha blending operations. At the heart of this system is the blend of various naphtha feed tanks to achieve a final product with a uniform density, ensuring consistency and quality for the downstream processes. The layout depicted in the graphic illustrates a meticulous arrangement of feed lines, flow control elements, and storage facilities, all intricately designed to harmonize the flow and qualities of naphtha from different sources. It is a dance of precision, with operators and automated systems collaborating to maintain the delicate balance required for optimal naphtha quality. By closely monitoring and adjusting the blend, the facility ensures that the processed naphtha meets the rigorous standards for further refinement or direct application. This slide highlights the importance of precision in the blending process, where consistency is not just desired but essential for the integrity of the product and the efficiency of the entire refinery operation. Here is an intricate web of the tank's quality tracking system developed by OMS. This sophisticated software casts a wide net across various modules and interfaces, integrating seamlessly with distributed databases and distributed control systems, DCS. The system operates in a PC-based, multi-user environment that capitalizes on a server-client architecture, ensuring multiple users can access real-time data and insights concurrently. At its core, the system features a neural network that estimates stream properties, a blended information management system, and a dynamic library with quality models and optimizers. It is designed to be customizable, sporting dedicated process data interfaces and displays, along with alarms, messaging, and reporting functionalities. The tank's quality tracking system exemplifies the constructive collaboration between technology and human oversight, providing a comprehensive toolkit for accurate monitoring and decision-making in tank quality management. It is a digital orchestra where every instrument plays a critical role, contributing to the harmony of operations and quality assurance in a modern refinery setting. This slide highlights the tank's quality tracking system's composition tracking feature. It is an analytical powerhouse that applies the principles of a CSTR, or constant stirred tank reactor, model to assume a well-mixed tank for accurate monitoring. The interface provides a clear, graphical representation of the current and historical tank composition, with the ability to track the segregation of individual components over time. The system offers an in-depth view of the material balance with timestamps, displaying crucial information such as source, product, total volumes, and specific densities. By visualizing the components' distribution within the tank, operators can effectively manage and predict the quality of the output, ensuring that the process aligns with expected standards. This real-time compositional data is vital for making informed decisions on the fly, optimizing blend operations, and maintaining consistent product quality. It is like having a microscopic view of the tank's molecular dance, allowing for precise adjustments and optimal control of the blending process. This slide displays the multi-tank's quality tracking display, a sophisticated tool for monitoring the quality of multiple tanks over time. It uses advanced nonlinear blend models to calculate and track the quality of contents in each tank. This tracking ensures that the blend quality meets the desired specifications. The display presents a series of historical charts that provide a visual history of various quality parameters like RVP, mono, RON, and distillation points, among others. These charts are an essential part of the system, allowing operators to see trends and patterns in the data, which is crucial for making informed decisions about future blending operations. The user-friendly system interface offers options to select tanks, set time intervals for data display, and even print charts for reporting or analysis purposes. With this real-time tracking capability, refineries can optimize their blending processes, reduce waste, ensure consistency in product quality, and respond swiftly to any deviations from the set quality targets. Here we illustrate the intricate network of the system architecture used in tracking tank qualities. At the heart of the setup is the GOMS TQTS server, which functions as the central hub for data and management. This server interacts across an Ethernet with various user stations, including those for administrators, planners, business managers, shift managers, and control engineers, signifying the system's broad user base. The architecture also integrates a distributed control system, DCS, highlighting the automation aspect of the system, which is vital for the real-time control of blending operations. Furthermore, a laboratory information management system, LIMS, is shown to be part of the structure, emphasizing the system's commitment to accurate data and quality control. The blending or unit operator, depicted with an icon of a worker at a computer terminal, represents the human interface with the system, ensuring that operations are monitored and adjusted as necessary. Switches and analyzers are depicted, underlining the real-time data collection crucial for product quality. This system architecture is a testament to the modern approach of blending operations, reflecting a highly distributed, interconnected, and automated environment, all working in concert to maintain optimal tank quality. It's an impressive blend of technology and human oversight, ensuring precision and efficiency in tracking tank qualities. This slide outlines the advanced capabilities of a model-based prediction system for managing fuel qualities, such as those in diesel, kerosene, and gasoline. This intelligent system can model over 70 qualities across various end products, ensuring a broad application scope. The system excels at real-time monitoring and adjusting, estimating quality changes due to various operational activities like inter-tank transfers, loading and unloading, rundown processes, and batch blending. This strategy is pivotal for maintaining consistency in product quality, especially during simultaneous operations that could otherwise affect the end product's properties. It utilizes current infrastructure, integrating seamlessly with existing online analyzers and laboratory analysis to evaluate the quality of tank inlet process streams. This is a testament to its adaptability and ease of integration. The system's configuration and commissioning process are impressively swift, promising users the ability to see benefits within 2 to 3 months. This quick turnaround is essential for businesses looking to improve their operations without significant downtime. Furthermore, the system offers continuous accessibility, providing quality information online 24/7 for all necessary applications. It is designed to work harmoniously with standalone optimizers and complex feed-forward and feedback systems, highlighting its versatility in various operational environments. This slide presents a robust, flexible solution for quality tracking, promising to enhance operational efficiency and product reliability through its sophisticated predictive capabilities. Here, we discuss a published case study highlighting the success of implementing an online tank quality tracking system in a Singapore refinery. The study delves into the system's design, development, and practical benefits as realized by the Singapore Refining Company, which operates with joint ownership by Chevron Texada and Singapore Petroleum Company. The report, featured in Hydrocarbon Asia magazine, underscores the tangible advantages of the Offsite Management System, OMS, to the refinery's operations. These benefits stem from the GOMS-TQTS, Tank Quality Tracking System, which provides real-time monitoring and management of tank qualities. This case study serves as a testament to the system's effectiveness, emphasizing its contribution to refining operations by offering a detailed analysis of the system's impact, including enhanced efficiency, improved quality control, and overall operational excellence. The case study also signifies the industry's recognition of advanced technology's role in modern refining and the potential for replication in other facilities seeking similar improvements. This slide overviews system parameters related to diesel and kerosene, (KERO) products within a tank quality tracking system. For both diesel and KERO, there are 8 product tanks utilized. Diesel features 3 rundown headers, while kerosene uses 2. The process streams number 7 for diesel and kerosene, indicating the pathways through which the product moves within the system. Regarding process tags, which are likely identifiers for various data points within the system, diesel has 220, while kerosene has a slightly lower number at 192. Both diesel and kerosene utilize online analyzers, with diesel having 7 and kerosene having 8. This suggests a robust monitoring setup to ensure quality control. Predicted qualities, which are likely forecasts or estimations of product specs based on the system's models, are given as 3 for diesel, covering 90% point, sulfur, and density, and 2 for kerosene, covering flash point and freeze point, highlighting the critical quality attributes for these products. Both product lines utilize nonlinear quality models, which implies sophisticated algorithms capable of handling complex, real-world, nonlinear relationships within the data. Custom process displays, with 9 for diesel and kerosene, suggest tailored interfaces for operators to monitor and control the blending process. Additionally, the slide shows quality parameters for different products, such as KERO JP5 and KERO Jet, with specified minimum and maximum thresholds for qualities like flash point and freeze point. This emphasizes the precision and safety standards in monitoring fuel quality. The slide indicates a well-equipped and finely tuned system that closely monitors and predicts the quality of diesel and kerosene products, ensuring they meet the necessary standards and specifications for their respective uses. Let us look at a concise overview of key performance indicators, KPIs, for the quality tracking of kerosene and diesel products in a refinery setting. It showcases the effectiveness of the tank's quality tracking system, GOMS-TQTS, by comparing quality deviations of products from their target specifications in 2001 and 2003. The average flashpoint quality deviation for kerosene products improved from 0.935 to 0.69, showing enhanced control over this safety-critical parameter with the implementation of GOM-TQTS. Additionally, the standard deviation decreased significantly, indicating more consistent quality. The freeze point deviation for kerosene also saw a slight improvement in the average deviation, but more notably, the standard deviation reduced, reflecting a tighter quality control and less variability in the product. When it comes to diesel, the 90% point quality deviation, which likely pertains to the distillation temperature, improved from an average of -2.19 to -1.74. While the standard deviation increased, this suggests that while the average quality moved closer to the target, the measurements might have a slightly wider spread. In summary, the introduction of GOM-TQTS has contributed positively to the refining process by reducing the average deviation from target specs and, in most cases, narrowing the variability, thus enhancing overall product quality consistency. This slide underscores the system's value in refining operations, emphasizing its impact on maintaining stringent quality standards for hydrocarbon products. Now, we compare the system's performance before and after implementing the tank's quality tracking system, TQTS. The graph visualizes lab-analyzed tank quality deviations from specifications in degrees Celsius for diesel tanks, comparing data from 2001 before TQTS implementation and 2003 data after TQTS. In 2001, the data points were more spread out, indicating a more considerable variance in quality deviation, with several instances of off-spec products and quality giveaways. However, in 2003, after the TQTS was implemented, we observed a tighter grouping of data points around the zero deviation mark. This suggests a significant improvement in maintaining tank qualities within the desired specifications. The reduction in giveaways and off-spec conditions indicates a more efficient and precise system, minimizing waste and enhancing the overall reliability of product quality. The implementation of TQTS seems to have successfully reduced the quality deviation, bringing more samples within the acceptable range and enhancing the consistency of the diesel products. This improvement not only suggests a direct positive impact on operational efficiency but also highlights the value of TQTS in quality control and product consistency within the refining process. This slide presents the positive outcomes of the tank's quality tracking system, TQTS, implemented by the Singapore Refining Company, SRC. The system, developed by Offsite Management Systems LLC, has been instrumental in optimizing SRC's blending operations for kero and diesel. The highlight is the financial gains the refinery has achieved through this system, estimating an impressive range of $2.5 to $4.4 million in annual tangible benefits. SRC has taken a conservative stance in claiming savings, acknowledging that 25 to 35% of these benefits can be credited directly to the implementation of GOM's TQTS. This conservative estimate speaks to the system's efficacy, as the refinery has experienced a rapid return on investment, with payback in less than 1 month. This slide underscores the transformative impact of integrating advanced tracking systems into refinery operations, leading to significant cost savings, efficiency improvements, and a swift return on investment, solidifying the case for investing in such technologies. To summarize this topic, emphasizing the advances in predictive technology for online measurement of tank qualities. This innovative approach has proved its value, showcasing its potential by providing round-the-clock monitoring of tank properties in both the refining and chemical industries. Notably, the technology is versatile, functioning efficiently in both open-loop and closed-loop systems and allowing for seamless integration. A significant enhancement is seen in the role of online analyzers. By optimizing their placement, the technology has increased their effectiveness, ensuring more accurate and timely data for operational decisions. This, in turn, has led to an impressive return on investment in under a month, with substantial financial benefits accruing annually for refineries processing 300,000 barrels per day. We conclude by highlighting this technology as not just a cost-saving measure but also a tool that brings about a paradigm shift in how tank quality control is perceived and managed within the industry.
Thank you, Dr. Suresh Agrawal. We have now concluded our presentation for Webinar 8. Our Academy has offered monthly webinars on fascinating subjects related to downstream refining operations. The necessity of choosing the proper process analyzers will be the topic of our upcoming webinar, the 9th in the Master Series, which takes place on December 20, 2023. We and our collaborator Modkin will host it. We will review the qualities analyzed in the refining sector, the kinds of analyzers employed for each quality, and how to install and choose them. Remember to set up an account on LinkedIn. We are beginning on December 1. We will now begin the question and answer session. You can email us any more questions at the email address below and the ones you posted in the conversation. We will ask you 2 poll questions for candid comments following the Q&A session. Would you kindly take a moment to respond, yes or no? First, is the absence of real-time tank quality an issue for your outdated batch blending systems? Second, would it be beneficial for your refinery to use model-based prediction to lower the lab analysis load? We will now begin the poll. We will close the poll now. Thanks for participating in the poll. Your answers will give us insight into our webinar content. Our complimentary gift is an ebook with 250 plus PA+Gs after you complete the survey. We provide a free 1-hour consultation with our academic director, the webinar presenter, Dr. Suresh Agrawal. Please take advantage of this chance to talk to him about any problems you are having in your refinery, or how to sign up with our academy to receive the benefits of eLearning. We hope to see you at the upcoming webinar. When you exit the webinar, it will lead you to the Google survey form where you may provide us with insightful comments. Thank you, and have an excellent remainder of your day or evening.